Hi class, in this short video I'm going to be giving us a little introduction to section 4.1 involving the basics of differential equations. Basics of differential equations. So we should start off first by talking about the definition of a differential equation. So the definition is that a differential equation is an equation that involves the derivative of an unknown function. Our goal in solving the differential equation, which we'll abbreviate DE, is to find that unknown function. So let me give you an example of what a differential equation looks like. Here's one example. dy dx equals e to the x squared over 2. Okay? So the derivative of the function y equals the function e to the x squared over 2. Our goal would be to figure out what function is y such that if I took its derivative, I would get e to the x squared over 2. Now, the interesting thing about differential equations is not all differential equations have a solution. If they do have a solution, it may be very difficult as well to find what that solution is. So this type of differential equation right here, we may have a really difficult time to try to solve it. Whereas something like this, dy dx equals x times y, that would be a very easy differential equation for us to solve. What I'm looking for here is the function y such that when I take its derivative, it's equal to the original function y times x. In other words, the action of taking the derivative of y simply multiplies the original function by x. So what kind of a function might have that behavior? Well, in fact, this function right here, e to the x squared over 2. A solution to this is y is e to the x squared over 2. And the reason that's a solution is, again, this. If I take the derivative of this, dy dx, differentiating this, I have to use the chain rule. It's going to be the original function, e to the x squared over 2, times the derivative of the function up in the power, the derivative of x squared over 2, is going to be x. And when I look back at this, what I see is dy dx is simply x times the original function. That's what I have here, x times the original function, y equals e to the x squared over 2. So there is a solution to this differential equation. Okay? All right, now when we're finding solutions, we have to distinguish between the concept of a general solution and what's called a particular solution. So let's try to explain what a general solution is to a differential equation. A general solution to a differential equation is the form of all possible solutions to the differential equation. Okay, so a general solution is really not a solution, it's a family of solutions. It's the form of all solutions. General solutions are the family of all solutions to a differential equation. Okay? On the other hand, a particular solution to a differential equation is a solution that not only is of that family, it is a general form solution, but it also satisfies some particular condition that has been imposed upon the differential equation. So a particular solution to a differential equation is of the form of the general solution, but also satisfies a particular condition that must be met. So let's look at an example of this. Let's take a very simple differential equation. Let's solve dy dx equals x. In other words, I want to know all functions y such that when I take their derivative, I get x. Okay? So the solution to this, and we'll talk more about how we actually find these solutions in detail in section 4.3. For now, when we're talking about the solution to a differential equation, we're just using basic reasoning of how we understand derivatives to work. Okay, we're not giving you a formal process of solving a differential equation until we get to section 4.3. For now, it is just our basic understanding of differentiation. So when I look at this and I say, okay, how would I find a solution? I think, okay, what would I take the derivative of that would give me x? Well, I know that 1/2 x squared, if I were to take the derivative of that, would be x. Therefore, that would be a solution to this differential equation. Now, any function of this form that has the same derivative as of x would also be a solution. So what we realize here is any constant added on to this, when this is differentiated, that constant will disappear, and I will be left with x as well. So this right here, then, is the general solution. Okay. Now, if one were to further impose upon this differential equation a particular condition that must be met, then we would call this an initial value problem. An initial value problem is a differential equation with a particular condition added on. So for example, if we were to say, let's solve dy dx equals x such that when y is evaluated at 0, we get 2. Then I would say, okay, the general solution to this is y is 1/2 x squared plus c, and then I would say, according to this initial condition constraint, that when I put in 0 for x, the value of y must be 2. Y must be 2 when I plug in 0 for x. That allows me to identify the value of c to be 2. So the particular solution is y equals 1/2 x squared plus 2. Okay. All right. So let's take a look at a couple of exercises in the book and see if we can reason through those. Okay. When we take a look at problem number 28, we're given y prime equals 3x plus e to the x, and we're asked for the general solution. That means the family of solutions to this differential equation. I want to know the function y that when I take its derivative, I get 3x plus e to the x. And again, the way we're going to reason through this at this point in the course is simply to think about differentiation as a process. I think, what would I take the derivative of to get 3x? And I would realize I should take the derivative of 3 halves x squared to get 3x. The 2 comes down, cancels the 2 in the denominator, leaves a 3x. Then I say, what do I take the derivative of to get e to the x? Well, the derivative of e to the x is e to the x. So there's a solution to this differential equation. The general form of it now is plus a constant, since that constant, when differentiated, would disappear. This is the family of all solutions to this given differential equation. In problem number 30, we're given y prime is sine of x times e to the cosine of x. So I have to think, what would I take the derivative of to give me sine of x times e to the cosine of x? Well, e to the cosine of x, when I differentiate that, is going to be e to the cosine of x times the derivative of cosine of x, which is negative sine of x. So if I put a negative in front of this, that will cancel the negative from the differentiation of the cosine of x, and I can then say the derivative of negative e to the cosine of x is sine of x e to the cosine of x. Add a constant, and this is the general form for all solutions to this differential equation. Do one more example, number 36. Y prime is equal to y. I want to know what function it is, so when I take its derivative, it gives me the same function back again. Well, what we know from differentiation is the following. The derivative of e to the x is e to the x. The derivative of a constant times e to the x is constant times e to the x. So this is the general form of the solution to this differential equation. And so what you notice is that constant that forms the family of solutions of that form, this time it's not added, it's a multiplier to this. Okay? And of course, you can add on another constant, right? That would disappear under differentiation, but it would not disappear on the left-hand side, so we can't have that under consideration there. Okay? The general form really is just this. Okay? Now let's look at the variation on this of the idea of an initial value problem. In number 38, we want to solve dy dt is 2t. And you may notice we switched to the dependent variable being t instead of x. That's commonly done in initial value problems. The initial condition that must be satisfied, y of 0 equals 1. So I want to know, what do I take the derivative of to give me 2t? Well, that would be t squared plus a constant. There's the general solution to that differential equation. Now applying this initial condition, when t is 0, the value of y is 1. 1 is 0 squared plus c, tells me that c is 1. My particular solution to this initial value problem, therefore, is y equals t squared plus 1. If we modify the initial value problem and say dy dt is 2t, same differential equation form, but now the initial condition is y of 0 is negative 1, the only thing that's going to change in the solution is the value of c. I find y, again, t squared plus c. I apply the initial condition now, and now y is negative 1 when I plug in a 0 for t. So c is negative 1, and my particular solution here to the initial value problem is now y is t squared minus 1. All right, so that's the basic idea of section 4.1. You're going to practice with finding some solutions to differential equations. You're going to verify that some functions that are given to you are indeed solutions of differential equations simply by differentiating and plugging into the equation. But what you're not going to do is worry too much about how you come up with the solution at this point. Okay? So as you do your exercises, you may notice that some of the exercises are a little more challenging in trying to find what the function is that's been differentiated. For example, if you look at problem number 32 or 34 in the exercises, you might be challenged to figure out what is the function that was differentiated to get this form. Okay? Don't worry about those at this point. Okay? Again, in section 4.3, we'll formally talk about how you actually find those solutions. Right? So give section 4.1 a try. Get comfortable with working with a solution to a differential equation. Get comfortable with the concept of solving an initial value problem, and you'll be ready to move on to section 4.2.